All right. So the next test that we're going to be talking about is the telescopic series. And it's still frozen, isn't it? There we go. All right, is the telescopic series. So it's a series, like the one they showed there, that kind of collapses on itself. So if we actually look at this, we have minuses and pluses all through here. We have 1 minus 1/2, then plus 1/2. So we see that those 1/2s are actually going to cancel. Then we have minus 1/3 plus 1/3. So the 1/3s are going to cancel. And if you keep listing out the series, everything's going to cancel, and what's going to be left over in this series?
1.
There's going to be a 1 left over in this series, yeah. So this series is a telescoping series, which actually means it's all collapsing down just to that 1. Everything's going to cancel out, it's collapsing to 1. So if a series collapses to a finite sum, then it converges by the telescoping series test. So let's actually take a look at some of these examples. So what's the first thing we always do when we get a problem like this? I mentioned it last week. First step always has to be, I know it's all the way back to Thursday, but I don't know, I heard some whispers over this way. Yeah, try the nth term test. That's the one we said we always try that first. So we actually need to take the limit here. So if we took the limit as n approaches infinity, that would actually equal what from this if we took the limit of this? Think about the first one and then the second one. What was that? 0. You're going to get 0 minus 0 equal to 0. So the nth term test tells us what? It's on the board too. Nth term test is inconclusive. It doesn't tell us convergence, it only tells us divergence. So it's inconclusive. The nth term test is inconclusive. Well, if you say that every time, by the end of this unit, you're going to have it memorized. So it's inconclusive. So now let's actually write out the telescopic series like they showed us in the example. So if we plug in 1, what is our first set? If we plug in 1 up here. Two times 1 is 1, plus 3, so we get 1/3. And then we plug in the one over here. We get 1/5, so it's actually going to be minus 1/5. So that's first. Then we're adding. Now we have to plug in 2. Well, 2 times 2 is 4, plus 1, so that's the 1/5. Plug in the 2 over here. 2 times 2 is 4, plus 3, so 1/7. But it's a minus. And we can list out one more. Plus, plug in the 3, you get 1/7. And then you plug in over here, you're going to get 1/9. And this pattern is just going to keep on going. So if we take a look at this pattern, the negative 1/5 and 1/5 cancel. The negative 1/7 and the 1/7 cancel. And if we continue to write this on, what can we assume? Yeah, that pattern's going to continue. Those are all going to cancel out, and it's going to collapse to what? The 1/3, yeah. So converges to 1/3 by telescoping series. So it converges to 1/3 by the telescoping series. Now I want to make sure you have that down because I'm going to erase that so I have room for the other examples. So, is everybody okay with that example? Any questions? Make sense so far? All right. Yeah, so far. All right. So let's look at B. B is a little trickier because it doesn't exactly look like the first one did with the plus and minus. But what are we going to start with first? Nth term test. So the limit as n approaches infinity. So if you take the limit of that, what is it going to be? Yeah, the limit is equal to 0. So what does that tell us?
Inconclusive.
It's inconclusive, yes. So nth term test is inconclusive. Inconclusive. Now we want to try this telescoping series. We see it kind of had the pattern like this, but this one looks different. Does anybody see a way that we might be able to make this problem look like the telescoping series or break it up? It's 2 words. First one starts with a P, second one with an F. Partial fractions. All right, so we're going to use partial fractions. Partial fractions. And we're going to use the method I know how to do this. Do you guys know the cover-up method for partial fractions? Okay. Do you guys know how to split this up? Okay, how would you go about splitting up using partial fractions?
Put A over N
Okay.
like as one part, and then B plus B over N plus 1.
Okay.
And then write an equation where it's like A, and then in parentheses N plus 1 plus B, where N is in parentheses, and then set it equal to the top, which is 1.
Okay, so I'm going to show you a method to reach the same thing, but it's called the cover-up method. So if you're looking at your denominator here, if you set this n equal to 0, well, you're just going to get 0. So you're going to cover up that one that we solved for 0 and plug in 0 to the rest of it. What are you left with? 1 over 1. So your A is going to be 1. Now, if you solve this one for 0, you're going to get n equal to what? Just this n plus 1 part. Negative 1. So cover up that part we used. Plug in negative 1. So B is negative 1. So if we actually apply this now, we're going to get the sum n equals 1 to infinity of, well, A is 1 over n. And then B was negative 1, so it changes to minus 1 over n plus 1.
How do you get A equals 1 again?
All right, so we have the A over the n.
Yeah.
So if I set n equal to 0, it's just going to be 0 when you solve. So now I cover that one up because that's the one I used. So plug that 0 in here.
Oh, okay.
0 plus 1 is 1. 1 over 1 is 1, so A is equal to 1. And then for the B, we solved n plus 1 equal to 0. You get negative 1. Now cover it up, plug in the negative 1 to everything that's left. You get 1 over negative 1, so now the B is negative 1. Okay? And then you plug in the 1, plug in the negative 1. So now we actually can use the telescoping series. It actually looks familiar now. So let's write out a few terms. I'm going to write them over here to the left. If we plug in a 1, we'll get a 1 minus This becomes 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus, and it's going to keep going on in that same pattern. So we see again the negative 1/2 and the 1/2 cancels. The negative 1/3 and the 1/3 cancel. And the pattern is going to continue, so we can assume once again that what is going to happen? Yeah, all of those terms are going to cancel out. The negative 1/4 would cancel out with the next term, and it will converge to that 1. So converges to 1 by telescoping test. All good with that example? Make sense so far? All right. I'm going to erase for the next example. Okay to erase? All right, so the third example, once again, looks different from the first two so far. So what do you think could be an important first step with this one, with the look it has? Yeah, we're going to factor the bottom. Anybody know what the factors are? N plus 1 and what?
N plus 2.
Not quite. What times 1 equals 3? What times 1 equals 3? 3. So we have n plus 3 and n plus 1. So we know the bottom can be factored, so let's go ahead before we move on, and what do we need to do first? The nth term test, yes. So by the nth term test, what do we know? The limit is equal to what? 0, once again. So by the nth term test, it is inconclusive. Yes, nth term test inconclusive. So you can go ahead and write that again. I'm going to save some space. I'm not going to write that again. But the nth term test is inconclusive. And then we already factored the bottom, but it still doesn't look like our telescoping series over here. So what do we need to try again with this example? Partial fractions. So let's set it up just like you did with the other example. And we'll try that cover-up method again. All right. So we need to, let's pick the n plus 3. So if you solve that for 0, negative 3. So now cover it up, plug in negative 3 to the rest of it. So a is negative 1/2. N plus 1, if you solve it when it's equal to 0, you get negative 1. So now cover it up, plug in negative 1 to what's left. So b is equal to 1/2. Now we can plug in. So we have our sum, n equals 1 to infinity, negative 1/2 over n plus 3, plus 1/2 over n plus 1. Now, I mean, what's a little different about this one that we could change, but we don't necessarily have to? What do you see about maybe notation?
Switch them.
If you wanted to, you could switch this so you have the minus in the middle. It doesn't really matter. It's going to work out either way, so I'm going to leave it the way it is, but you can switch it if you want to. So what you have to do now is list out the terms. So if we plug in starting with 1, you're going to get negative 1 what for the first one? Negative 1 over. Yep, negative 1/8. And then for the next one, you're going to get plus 1/4. And you really have to pay attention to this one because the pattern is not normal. The next one, we're going to get negative 1/10 plus 1/6. So far, has anything canceled? So right now it's not looking like it's a telescoping series, but let's continue on. Plus negative 1 over 12 plus 1/8. Let's go a little further. Plus negative 1 over 14 plus 1 over 10. Are we starting to get any cancel? Yeah, so we have had the negative 1/8 cancel, and the negative 1/10 and the 1/10 cancel. Let's go one more term, see if anything else cancels. Negative 1 over 16 plus 1 over 12. So I'm going to cross these out. The negative 1/8 and the 1/8 canceled. Negative 1/10 and the 1/10 canceled. This negative 1/12 and that 1/12 canceled with what we just wrote. So can we find any kind of pattern, or do we need to write out one or two more terms?
I think it converges to 1/4.
Okay, we have the 1/4 here. We still have a 1/6 here that hasn't canceled yet. We still have a negative 1/14 here. So let's go one more term and see which cancels next. So the next term, we have negative 1 over 18 plus 1 over 14. And sorry, I'm going off the page there. But that's negative 1 over 18 plus 1 over 14 is the next term. So actually, the next term to cancel was the 1 over 14 and the negative 1 over 14. And if you have room, yeah, go ahead.
Would it converge to the combination of the 1/4 and 1/6?
Exactly. So if you're writing out the next term, I don't have room to write it. If you want to write the next term, it's plus negative 1 over 20 plus 1 over 16. So that's the next term. So then your 1 over 16s cancel. So we're going to keep going on and on. Well, that 1/4 from up here never canceled, and this 1/6 is never going to cancel. Those two were left behind together. So if you add them together, what are you actually getting your convergence to?
5/12.
Yeah, exactly. So just because there's two terms left doesn't mean it doesn't converge. It converges to the sum of those two. Because you can keep adding terms on in this series, and that 1/6 and 1/4 will never cancel. Now, this series looks a little different from the first two, but it's still a telescopic series because as you go on, you're still canceling and it's going to collapse down to some finite sum. Okay with that? All right. So that's pretty much it for the telescopic series. So what we're going to go to next, I believe in your notes should be next, is the integral test. Is that what's next? All right. All right, so the integral test. If f is decreasing, continuous, and positive for x greater than or equal to 1, and your an is equal to f of x, then the sum of your an and the integral, and it's important that these here have to be the same. So your lower bound for your integral and your sum and the upper bound, they're going to be the same. They either both converge or they both diverge. So what kind of test could we call this one? We have one of each up here. So this test would be considered a two-way test. Because we're going to be able to tell whether it converges or diverges.
So for the telescopic series, was that two-way or one-way?
What do you guys think?
One.
It was a one-way. Actually, sorry. If you look back at that, what do the directions for example 10 say?
Yeah, that's what was confusing. So it says like a convergence or divergence.
Yeah, our examples all did what?
They all converge.
They converged. But if you're going to get a sum that something is continuously being added on and doesn't cancel out,
Yeah.
you would have a diverging series. Yeah. Sorry about that. But once again, if you're doing this, you've already checked it with what test first? So does it really matter? You've already determined that it diverges by the nth term test. So
That, like, are you
if it does, you're just confirming with the telescopic series that it does converge, and you're figuring out what it converges to.
Okay.
Okay? Does that help out? All right, so back to the integral test. I think lastly I said the bounds have to be the same for your summation and your integral. But this does not mean, so that's important right there, that the series converges to the value of the definite integral. So just because you get a value does not mean that it converges to that value. And then at the bottom we have this part here, which it's going to sound confusing now, but once we get to a later example, it'll make a little more sense. But the series, if the series converges to S, then the remainder, Rn, is going to be equal to the absolute value of S minus Sn, which is bounded by this from 0 to your integral. So basically it's talking about an error. So it's going to tell you that your sum is within these bounds. So we don't know exactly what this sum is going to be, but we know if the sum converges, we're going to be able to find some bounds with some amount of error that we know it's going to be contained within. So if we go right to the example, determine whether the following series converges or diverges. If they converge, find the interval in which the sum resides using S4. All right, so for the first part, what's the first test we always use? Yep, nth term test. So limit as n approaches infinity. The limit of this one, is it 0 or is it not equal to 0? Think of it as n over n squared, and if you have n over n squared, it simplifies to 1 over n. So the limit would be what? 0. So once again, nth term test, inconclusive. Nth term test is inconclusive. So now what we actually have to do, we have the summation, we need to do the integral with the same bounds. So we're going to have the integral from 1 to infinity. And you don't have to, but some of the way the examples are written out, you may recognize the integral if you change the n to an x. So since we're doing the integral, let's change that n to an x. So we have x over x squared plus 1, and then we would have our dx. That way we have terms we're familiar with. Does anybody recognize this integral? Or know what the integral is?
Arctangent?
You're close. The arctangent would have a what on top though? A 1. So it can't be arctan. What about natural log? You figure out how to use the natural log for this integral? Alright, so if you think about that, if you have a natural log and you take the derivative of a natural log, how do you take the derivative of a natural log?
1 over x.
Well, you would have 1 over what's inside times the derivative of the inside. So we know that the inside, if we're using natural log, it's going to be x squared plus 1. But when we take the derivative, we need to make sure that it looks like this. So do we need any type of correction factor or anything? So if you take the derivative of this, it'd be 1 over this times the derivative of the inside. Well, what's the derivative of the inside? 2x. But over here we just have a yeah, exactly. So our correction factor is 1/2. That would cancel out the 2. And that's it. Our bounds are from 1 to infinity. That's the integral of that. So now let's actually evaluate the integral. That should be 1. So the 1/2 ln of infinity minus 1/2 ln of 2. Any guesses? Does it diverge or converge? Yep, this is actually diverges. So if this diverges by this test, what do we know? So since the integral of x over x squared plus 1 dx diverges, yep, so does the sum from n equals 1 to infinity n over n squared plus 1. So if you test 1 and it works, then you know, or the integral and it works, diverges or converges, then you know that the series also either converges or diverges. What time is this class over?
56.
All right, next example. So this part here, what we're actually using is just the top part of the integral test. We have not done this yet, and we're not going to actually do it on these two examples. We're going to wait till example 12 to actually go through that process, so it'll be something completely separate. So right now all we're using is the top part of the integral test, okay? We aren't worrying about the error yet. We'll introduce that next. Alright, so the next one. Again, start with the nth term test. Limit as n approaches infinity. This one is like 1 over n squared, so the limit is 0. So once again, you can write the nth term test is inconclusive. You don't know what's happening. And since it's inconclusive, look, we can set up the integral test. Once again, I'm going to make it look familiar with x's, so we can have our dx. Everything looks familiar. Does this integral seem familiar? Yeah, this one has the 1 on top. This is the arctan. Arctan of x from 1 to infinity. If you plug in infinity, what is arctan approaching? Pi over 2. Yep. And arctan of 1, you'd actually get minus pi over 4. When you subtract those, you get what as your answer? Pi over 4. So does it diverge or converge? Converges. Does that mean that your series converges to pi over 4? No, you're correct. It doesn't. This means that it converges, but it does not converge to the definite integral. So since integral from 1 to infinity of 1 over x squared plus 1 dx converges, so does the sum from 1 to infinity of 1 over n squared plus 1. So we know by the integral test. Now you could state by the integral test, we know that it converges or diverges, but you were showing your actual integral, but on a test or on an exam, if it asks you to state the test, just make sure that you would state it in your answer. Like we always state at the top, by the nth term test it's inconclusive, so they know that you use that test. The integral test, yes, you're actually taking the integral, but if they ask you to state it, make sure you state it. Any questions? We're going to leave the error bound for tomorrow, because we need some time to talk about that one, and we'll run out of time today. So tomorrow we will pick up where we left off.